So one of the advantages of being the last one in the day is that you get to see everybody before you and modify your slides a little bit. So I've added this. So I'm from Salesforce. Those of you who do anything in NLP probably heard of a guy named Richard Socher. He's chief scientist in Salesforce. We do a lot of stuff with deep learning. None of it will be covered this talk. So seeing that I was late a little bit, if you still want to stay here, that's fine. If you want to find another deep learning talk, that's good, okay. Great. All right. Half the money I spend on advertising is wasted. The trouble is I don't know which half. This well-known phrase was termed about a century ago. And in a survey relatively recently that was done across various leading marketers, they discovered that it's, pretty much holds true today. So that's 50 cents of every dollar unaccounted for. So how many dollars do we have there? So in 2017, global marketing, that's advertising and media and everything else, budget crossed $1 trillion. That's a lot of 50 cents. And the work I'm going to present today has been used, applied to try and solve this conundrum, or at least advance where we stand today. But before I jump there, I just want to say a few words about Salesforce. By way of background, I've joined Salesforce in 2016 through an acquisition of a startup at the time called Crux. There's certain things I knew about Salesforce before I joined. I knew it's an enterprise software company. It's in the B2B marketing space. It does customer relationship management. But there's certain things I didn't know. I didn't know, for example, that Salesforce was indeed the fastest growing enterprise software company out there. We've crossed 10 billion last year. We've guided the market for 12 billion this year. And Mark Benioff, our CEO, has hinted at 20 billion just around the corner. And the key reason why we're growing so fast is because Salesforce is, in fact, these days, much, much, much more than just a B2B CRM system. So the vision we have at Salesforce is that, we want to become the center, the hub for managing all of the interactions, our clients, companies like Hotels.com and Adidas and Kellogg's and L'Oreal and New York Times and Fox and many of the household brands we all know about, helping them manage their relationship with their customers. So that's B2B and B2C. We have one of the biggest e-commerce platforms in the world. We have a lot of work done on IoT. We have the leading service platform in the world. And, of course, Marketing Cloud, where I spend my time. In the last couple of years, Salesforce also doubled down on this data science, AI, machine learning space, a series of acquisitions, and homegrown. The brand name for all things data science in Salesforce is Einstein. And we've infused a lot of Einstein in all the different clouds. I'll call out Sales Cloud, where things like predictive scoring, lead scoring, opportunity scoring. There's a bunch of work around surfacing news, relevant news to different clients. That team is all here in Israel. Also a series of acquisitions and some more hiring. And if you went through the booth today downstairs, we had a Salesforce booth there too. Okay, so that's all I wanted to say about Salesforce. Let's go back to marketing and the motivation of the problem I've introduced at the start. The truth is today we all interact, engage with the world around us in, a plethora of ways, devices and mediums and channels. We also vary in when and how and what time of day we interact with. Let's suppose I'm a marketer for the Marketing Cloud at Salesforce. I want to drive people to purchase some of our products. I'm going to run some campaigns. I'm going to put ads in various places. I'm going to put some on the site, some in emails. I'm going to create some video content that will appear at different places. Let's say I've put out there about 8 different ways in which I want to send the message out. Any one of the users that has been exposed to my marketing efforts probably been exposed to one or more of those. And the key question that we want to answer is, what's the effectiveness of any one of those? Right? And the way you should think about it is, let's say the video campaign that I've put out. Maybe people that watched my video and weren't engaged by any other means have not ended up buying my product, but those that viewed my video and some of the other mediums have ended up going purchasing, right? So I want to really discover this interrelationship of all these things together, so I can go back and say what eventually worked and what didn't. Now, in this case, we have 8 different things. One naive approach would say, oh, well, look at all possible combinations and then go out there and test these things. If I have 8 things, I want to, test the combinations across that 256. But maybe not that bad. But if I want to break down those 8 and maybe look at other aspects of them, those that were served on a mobile device versus those that were served on an iPad or something else, those that were served at nighttime versus daytime, weekend versus weekdays, I can easily add more features there. If I have 20 different attributes that I want to test, well, that will be over 1 million. In our case, most real-life scenarios we've met, we had over 140,000 attributes to test every time. That's a lot of combinatorics. So it turns out that, in fact, in a sort of a classic applied mathematics 101, you go to the problem, it's too big, you go and look what others have done out there. So frequent pattern and associative rules mining, these are the 2 classic techniques that are applied to these combinatorial problems. And I mean, some of the initial insights you might gain is that clearly, not all of these combinations necessarily realize in the data. So I definitely don't have to account for all of them. And some of them are not there in any significant numbers. So I might have a threshold that I'm going to set to say, hey, if there's less than that, don't worry about it. So let's go back to the example and see how we map that into this frequent pattern and associative rules. I can give them letters just to make it easier. And I can certainly construct tables that look like that. I have users and then the sort of combination of things they've been exposed to. We can forget about sequence right now, although this is part of the real problem, but we don't have to worry about sequences. All right, now I can go and definitely count for every single unique item out there, how common, what's the frequency. We also call that support. I can do that for things that are of length 2. Mean support is the term I'm going to use for that threshold we've mentioned. And if the mean support is set up to 4, then some of the things are starting to get filtered out. We'll call the one that are of length 1, L1, and then L2 and so forth. That's a very important, it's actually a theorem, it's easy to prove, a priori principle. So one of the first observations that were made here is that all sub-patterns of a frequent pattern are also frequent, right? And it's quite easy to reason with. If E in this case doesn't cross the threshold, then any pattern that is built with the item E will not cross the threshold either. And if it's 6, you can see the same, right? And we will see how we come back to a priori principle later on. Okay, so there were a few algorithms that use this a priori principle to trim the tree as we grow. For example, you can imagine you can start, do one scan, find the L1s, then do another scan, find the L2s. The only ones you need to look for L2s are the items that appeared in L1. And by induction, if you keep on going, you're gonna converge. But the problem that that brings up, which links a little bit to the keynote from Matti we heard this morning, is a repeated pass over the data. That's highly inefficient. Can we do better? And the answer is yes. And FP growth is one of those methods. They came up with a sufficient structure, data structure, that takes 2 passes over the full data set to construct, and then you don't have to worry about the full data set anymore. You can work with these alternative structures. It's a tree and what we call a header table, which is as you will identify the L1 we saw before, sorted descending in terms of support. And then this idea of a linked list. Those dotted lines over there is a linked list of those items into the tree. So this is the header. This is how you link them. And something to observe, numbers in the different inside the tree are sort of the counts on that particular branch. They're strictly descending or monotonically descending over there, and that if certain items are higher than so for example in this case A and B are higher on the descending list in terms of frequency, they will always appear higher on the tree. Okay, how do you mine? So once you got this structure, now you want to mine the patterns out of it. It's an iterative process. That's probably the more expensive part of the algorithm. The key thing here is this diamond in the middle. It's the iterative, stopper. We're going to keep on projecting the tree until we end up with a single path or a single branch, and once we get that, then we can just mine that one itself. So let's see an example how we do that. We might start with, this tree is clearly not a single branch. So I'm on the no path. Let's start with a C as an example. I might project it to find the tree that is related to the C. These are clearly the 3 branches that it's evolved in. So the overall frequency for C is 6. We'll find those particular branches. We'll derive from that particular data structure that is relevant for that, construct a tree again from those. This is now, this structure there on the right is indeed a single branch, and now I can mine that to produce, so I'm on the yes branch here in the algorithm, and I can mine that to produce the respective patterns that are associated with C. And the beauty of that is I could keep on projecting that. If C wasn't ending up in a single branch, I can keep on projecting those resulting trees, and in an iterative way, I can just traverse the whole thing. Okay, so that's where the current state of the art was when we took over. And then theory meets reality, and like always, it doesn't always work. In particular, there's a few contributions we needed to do to advance where the algorithm was. We're not going to be able to cover all of them today, but I'm going to call out these two quickly, the differential minimum support and the compact results. So very briefly, they're really about the fact that if you think about it, that mean support, that single threshold is a very big limitation. It works well if all items come from relatively similar types of underlying statistics about how common and how frequent they exist. Don't forget the frequent pattern was applied a lot of the time, this notion of basket analysis. You go through the supermarket, you pick up items. In that sort of scenario, you might buy certain things once a day, maybe once a week, other ones, but there's not going to be something in your basket there that necessarily you'd buy once a year or once maybe in a lifetime. These are very rare. Similarly here, when we started to looking at the data, we had clearly buckets of data that were very, very common, things that appeared 3 or 4 orders of magnitude more commonly than other stuff. So a single threshold meant that we were either not catching the rare things or catching too much of the very common things and losing a lot of the signal to noise. So we needed to approach that, and that's the differential minimum support work. There's all patents out there. The compact result set is about how do we avoid unnecessary combinatorics. But what I want to concentrate on for the rest of this talk is a little bit of that distributed frequent pattern and how we've done that. And the idea there is that everything you've seen so far requires that you can pass through the data in its entirety and that you can construct that tree and put it in memory. In our case, that wasn't, both of those didn't hold. We were not able, in reasonable time to pass through, twice even for the whole data, and certainly we couldn't hold those resulting trees in memory. So we needed to address that, scaling up. So here again is the example we have, the data coming in, the header and the graph. And the first observation we made is that the size of this graph is in fact determined by two factors: the number of rows in the original data set and the number of items, or the breadth of those rows. And while we can't shrink both of them at the same time, addressing one dimension at a time is a good way to distribute. You can't just simply distribute the data uniformly. You're going to end up with, the min support is a global operator, and you need to operate it globally on a full data set, on a tree. Okay, so then if we can either reduce the number of rows or reduce the number of items in a row overall, then we'll be good. As long as we don't have both, we'll be fine. And the way we do that is by, observing the fact that, further up that hierarchical L1 list, you'll find things that are very common, but those things that are very common will appear in relatively shorter rows, whereas the things that are rarer down the bottom will appear in longer rows, but there'll be fewer rows of them. So very similarly to how we projected the tree initially, we can keep on doing projections of the tree using that analogy and end up with results that look like this. So if I just distribute it based on that list that I have before, you'll notice that rows, if I remove, if I'm going for the longer rows that include all items, I'm going to end up with fewer rows in the data set. But if I'm removing now items and concentrate on the short end, we're going to end up with longer number of rows, but shorter item sets. Okay. Those projection trees can keep on being projected, again, the same as we talked before. So there is a way that you can iteratively go over that case. All right, so here it is after the distribution stage. We're going to have things with high number of items but low number of rows, and vice versa. We'll do that in a way that avoids that red X. Okay, and the implementation of it is fairly straightforward. I mean, in code as well, we build the FP tree header, we distribute the row executor, and we build the FP tree for each node and mine the patterns. We might have to do step 1 and 2 a few times until we go on to build, keep on projecting, and then collect the patterns at the end. This is a little bit how the architecture looks. And here, the couple of steps in the middle, those category classifiers, these are all related to that differential support that I discussed earlier on briefly. But the last few steps are what's important. Okay, so this is about mining the patterns. So now, if we look at it and the layer a little bit higher, what we've done here is we've done an extensive correlation study of the data, right? We've bubbled up to the surface anything that, those patterns, those coexisting patterns that exist in high enough densities. And with these other tools we had, hopefully we've minimized them to a number that is sort of palatable. But that still doesn't answer the whole question of value and effectiveness. It just means that there's things that appear together more often than others. What can we do with that? And the insight we had there is from game theory. So there's this notion of Shapley value in game theory. It actually was developed in organizational game theory. The thing they were trying to solve there is to assign a value to a player in a team, or an employer in an organization. And with very basic, as you do always in game theory, with very basic assumptions about what's correct or not. Things like, you can't have value out of nothing. And if I have a positive value somewhere, then removing me from the system should remove some value from the system, and assumptions like that. Things that you'd expect. With very basic assumptions, you can end up with an equation that looks like that, which is the closed form. So we have a game. And the game has n players, and V is the value function that maps any subset of players into a real value. Okay, so we can take any, think about a power set, any sub-selection out of those players and assign a value to them. And the idea there is that, you might want to assign a value to me for example, for Salesforce. You'll take me out of Salesforce, you'll put me back in Salesforce, and you'll measure some delta at Salesforce. But it might be that if I show up at work tomorrow, somebody else there might work better as well. So then you need to take both of us out, put both of us in, and by extension, you have to do that in the whole combinatorial space. So that's where the 2 to the n comes in. And the equation is also fairly straightforward. There's some normalization. There is, some form of, combinatorics factor here. So this is the choose to say how many ways you can realize any one of those subsets. And then the value is basically the one with and without that element. So that's how I attribute value to element I, one of the players in N. And the crux of the matter here actually is the summation here, because it's a summation over the power sets. So if we have millions of players, that's starting to get very tough. So to do it properly, you really need that understanding of the underlying correlation space. But we just found one a moment ago. So we have the structure that we've bubbled up through the frequent pattern analysis that shows us a whole lot about how the thing is correlated, and we have only the important ones out of all of them. So we don't have to waste cycle going through a summation over combinatorics that don't really exist. So combining this with the frequent pattern, we were able to assign value to every one of those marketing and come up with this relatively novel approach to attribution. So that's what I had as far as technical. But just to put the cherry on top, we have launched a product. In fact, it's been in market for a bit. And it's quite successful. I mean, some interesting, apart from going live and seeing it work in production and all of that good stuff, it's also good to hear sometimes from clients and say what they use it for and how it helps them. We have a client, one of our clients in the travel space. They spend a lot of money on what is called affiliates. Affiliates are these links, these other sites you pay to send you leads into your sites. And it turned out, using a tool, that they discovered that doesn't matter how you incorporate affiliates in your marketing campaign, they actually impact negatively the chance of you making any outcome from it. We had another client that had spent a lot of money on video over the years, and using the tool again, discovered that video works, but only works if it's combined with a couple of other things, like one of the visits to one of their sites. And so they subsequently went and spent a lot of money on the site, making it more effective. And we've seen also clients redistribute the budgets using this, people that skew towards one end now distribute it differently. And with that, I think this clock is correct. We definitely started a bit later, but I will leave a minute or two for questions. So that's all I had. Questions? So 3 things we did. We had to come up with a way to distribute it properly. It doesn't exist out of the box. I mean, we wrote everything from scratch. We didn't use any libraries, but there wasn't any way to distribute it in an efficient way working on big data. The original was very much tailored around database type use cases. There was no way to account for the fact that when you look deeply into how those patterns are constructed, the fact that you have a single threshold in minimum support does not going to help you in cases where there's categorically a whole bunch of items there that come from things that are very frequent. So things, for example, site visits. Visits to sites are very frequent, right? In the same time, think about, let's take the automotive industry. Lots of people visit their site, Peugeot, which is a client. A lot of people visit their site and look at cars or whatever, but buying a car is a very rare event. If I want to try and figure out, the interactions between various aspects of the site, versions of the site, different pages on the site, and, buying a car, ultimately, if I'm going to set up, and I want to do that through using frequent patterns, sort of a real boiling sort of bottom up, if I set up the threshold too low, I'm certainly going to catch those rare events, but I'm also going to catch up a lot of noise. Most of the patterns I'm going to spit out are going to be all about site visits, and I'm going to really need to hone in on the needles where something else exists. But if I crank it up too high to remove the noise, then I'm going to lose those rare events over there. So I got to combine them both together, and we do that by what we call differential support. We have a machine learning algorithm that classifies the different items based on the underlying statistics of occurrences into these categories. And then for each category, we're going to set a different threshold. Now, that's all good, but when it comes to the algorithm, when you need to assess whether a certain pattern is common or not, you have to still respect the a priori principle. So we needed to extend the a priori principle and show that, by setting those different thresholds now and making them consistent through the a priori principle, we're managing to be still complete and consistent with the original algorithm. So that's one extension we've done. And the third extension we've done here, at least, is this notion of the compact result set, which is, I termed it epsilon closure. A lot of the times you'll get, out of the box, you'll get those cases where you get a lot of patterns all related to the same branch, but breaking down. So you'll get, if you have a long branch like A, B, C, D, E, you'll get all the different breakdowns. But it could be that the support for all of those are the same. So in fact, most times you expect adding items to a pattern will decrease the overall support that exists in the data set, but sometimes it stays constant. So we wanted a way to minimize the occurrences of all these noisy things in the middle. We termed this epsilon closure, and we incorporated it into the FP growth as well. Does that help? That was a long answer. Now I'm definitely out of time. Yes?
How did the Apache Spark help you?
So I know that was a bit of a wild throw there. So we were early adopters of Spark way back, and everything we built is in Spark. So this was on Spark as well. I think if the alternative at the time at least would have been a MapReduce type framework. And there's a lot of recursiveness in here. And a standard MapReduce framework would be very tough to manage without recursiveness. You couldn't do it in a simple one job. You couldn't add those steps. You'd have to keep on writing to disk and reading back. It'd be a nightmare. Okay. Thank you.